Bismillahirrahmanirrahim. Uh, we in the last two lectures we discussed two-view geometry, the geometry of stereo images, and in particular we found out that there is a very important constraint there, which is termed the epipolar constraint, which helps in matching the points. And then while deriving the epipolar constraint in mathematical form, we saw that it's encapsulated in two types of matrices, the essential matrix and the fundamental matrix. The essential matrix is a relationship between a point in one image and a line in the other image, given that the measurements are done in real world coordinates, and then fundamental matrix is its form where the pixel coordinates are used. Okay, so the epipolar constraint is encapsulated within the fundamental matrix, and you can use the fundamental matrix also. So you can estimate. We looked at how we can estimate the fundamental matrix using a least squared solution. You have to find the null vector of a particular matrix, and we also saw that how you can find the epipoles, for example, from the fundamental matrix, or given one point, how you can find the line in the other image, given the fundamental matrix. Okay, so I did not go into too much detail of stereo. I just want you to be familiar with the notation and the objects here, how the mathematics is set up. You can do further reading if you want to. There are many stereo methods. There are many constraints on the matching strategies that people use, and it's something that works quite well. In fact, people use stereo to use cameras as a very detailed measurement device. Okay, 3D measurement device. So, for example, I saw an application where they were doing they had propeller blades of a ship, okay, and they want to check whether any crack has developed in them. So they put them in a setup. They have kind of a stereo setup. It's actually not two cameras. They use one camera and one light source, but that can also be formulated as stereo. So it's called structured light representation, structured light formulation, and that can also be done as stereo. And using structured light in a calibrated setup, they were doing very precise sub-millimeter measurements of the deformations of the blade and so on. Okay, so that's possible. I'm just telling you the accuracy with which, given the right setup, the accuracy with which such a setup can work. If you guys remember, this device, Microsoft Kinect, where you can play games. Okay, so the first version of Kinect with Xbox One was based on structured light. So which means it has a light source. You don't see it because it's an infrared light source. The way stereo works there is that you have a light source. The light source throws out a pattern. That pattern, if it illuminates a flat wall, it will fall on that pattern. And the other camera, there's a baseline between the light source and the camera, which is calibrated, and the camera detects that pattern. Okay, so if it's falling on a flat object, there will be one sort of pattern. If it's falling on a non-flat object, a 3D shape, the pattern will be distorted, and that distortion is detected. Okay, so that's a structured light reconstruction, which was done by Microsoft Kinect, and the new version of Kinect does not use that principle. It uses time of flight principle. So light ray goes out and it comes back, and there is a delay in it coming back. Of course, it happens very fast, but that delay can be measured as a phase difference in the waveform. So that introduces a phase shift in the waveform, and that phase shift is detected. So it's actually a highly advanced sensor. Before Microsoft came up with these sensors, these time of flight sensors were extremely expensive and of very low resolution. So they actually not only made significant advances to make it into a very high resolution sensor, but they also made significant advances, technological advances in making it in a very low cost way. Okay. The current iPhone X sensor is also very advanced. I'm actually not sure if it is time of flight or structured light, but I think it's a structured light sensor. I guess I'll check. But this structured light formulation is a stereo formulation really, except instead of having two cameras, you have a light source and a camera. So the mathematics changes slightly, but it is almost equivalent to stereo case. Okay. All right, so we are going to discuss a different type of multi-view geometry problem now, which is a structure for motion problem. And I showed you this video last time, which highlights what we want to do in this problem. Okay, so basically the input is a video. And in that video, you have some method. Like I said, we'll discuss those methods in the next module. You have some method to track points. So you find that, okay, let's say you have 100 points in the first image, then you find out where those 100 points are in the next image, and then where they are in the next image. So you get a bunch of observations from that video. So the structure for motion methods is take those observations, the image observations of moving points. That's why we call it structure from motion, because the points are in motion in 2D. But I can resolve their 2D motion into 3D points. Okay, and the formulation I'm showing you right now is rigid structure for motion, which means the points themselves in 3D are not going to move. So all the observations are of a static point. Okay, and then you can resolve that into 3D structure. Why? Because how much the points move as your camera moves, how much the points move is a function of depth, is a function of the 3D location. If the points were really far away and the camera moved like this, they wouldn't move much. Okay, but if they're close, they would move more, and so on. Okay, so so that's what we want to formulate now. That's what we want to see how this works. Okay, so this problem is I said there are a bunch of shape from X formulations. So we saw shape from two images, shape from stereo. And now this is shape from motion. It's called structure from motion, but it's really shape from motion. And then you can have shape from texture or shape from focus and many different things. But both of these, stereo as well as structure from motion, they actually work very well, and you can get high quality results from them in general scenarios. Okay. All right. So what is structure? In general, structure is a four-dimensional entity, okay? Because there is the X, Y, and Z axis. It's a 3D point, but the point can deform over time, okay? So that's why it's a four-dimensional entity. You have a set of 3D points in at the first time instant, and then you have a set of 3D points in the second time instance, and you have a set of 3D points in the third time instance, and so on. Okay, so that's why it's a four-dimensional vector. Now, if structure does not deform over time, which means it's rigid, then it's a 3D structure. Otherwise, it's a 4D structure. So that's the difference between rigid structure for motion and non-rigid structure for motion. Okay. Now, why do so we call dynamic structure, which means structure that deforms over time, is four-dimensional. Okay, which is your axis here, X, Y, Z, and time. All right. So now we are doing structure from motion. So structure, you understand. I mean, structure exists in the world regardless of whether there is a camera or not. Okay. Now, what is motion? So motion happens because of two reasons, right? One, that the camera is static, but the objects are moving. Okay, so that induces an image motion, like these cars moving in the image. But objects do not have to be moving to have induced motion in the image, right? So for example, this tree here is completely static, but if you look at each point of the tree, it's moving. Okay, and it's moving because the camera is moving. Okay, now if this object was planar, we understand that motion of how it will move. If this object was planar, the motion of all the points in the image can be described by a homography, right? I mean, yeah, We have seen that again and again. You have done homework on it, so we know that now. That the motion of all the points, if this object was planar, like just the ground here maybe, if the object was planar, motion of all the points is describable by a homography. But in this case, it's not, right? Notice how disparity changes because this this branch of the tree is closer to that, is closer to the camera than that branch, and so on. So it moves across as we move the camera around it. It moves across. Okay. So our objective is that given motion like this, we can somehow just look at how these branches are moving, just the 2D observations, how these branches are moving, and resolve that into structure automatically. Okay, and then of course you can have cases where you have both image motion and object motion. Okay, I mean camera motion, both object motion and camera motion. Okay, now in this case, this is really hard. Why? I mean, this resolving structure of this problem is really hard. And why is that? Because look at the hand of this guy, right? So in the image, it's going to form a trajectory like this. I'm tracing it. I mean, look at my pointer. I'm kind of tracing it. It forms a very weird trajectory in the image. Okay. Now, what do I have to do? If I want to find the 3D structure and its dynamic changing structure, if I want to do that, I have to take that 2D trajectory and resolve out of it actually 3 sets of unknowns. One, what is structure? Second, how is that structure deforming over time? Because it's moving because the structure was deforming over time. Okay. But then also, where is the camera? Because if the structure was not deforming over time and the camera moved, still the hand was going to move. But now the hand is moving, and it's moving in the image because of a combination of the camera moving as well as the structure moving, right? So it's a really hard problem. This sequence, by the way, we used in one of our papers, work done here at LAMS, where we showed that we were able to reconstruct it, and that was one of the first times that such deformable, highly deformable structure was being reconstructed. That's why we chose this scene. Actually, there are a bunch of reasons why we chose this scene. Our method was not so stable if the camera motion is small. So we actually wanted large camera motion, and this is an ideal sequence. The director spins the camera all around the actor. And then the actor is also doing like amazing deformations, which you normally don't find. So we had deformations like this in acrobatic videos and so on, but then the camera was pretty much static. And the way our method worked, we wanted both, we wanted the camera to move a lot actually. And so that's why we chose this sequence. It's not accidental that, in fact, when you look at results in computer vision papers and they show you results on all sorts of images, oftentimes it's not accidental that they chose those images. There's something specific in their method to which those images are favorable. Okay. By the way, it's also interesting how they shot this sequence. It wasn't that they were spinning a camera around this actor. You can go look up. There are a bunch of sequences like this in this movie where the director just wanted this effect of the camera spinning around the actor. And they actually put like maybe I think 32 cameras around the actor, which were static cameras. And they shot simultaneously from those cameras. And the actor is actually on strings because a human cannot do this action, right? It's a superhuman type of action. So the actor did this. They shot the video simultaneously from a bunch of cameras, and then they view interpolated. So there is quite a sophisticated view interpolation technique. So you know this is the view in camera 1 and this is the view in camera 2, and so you actually compute the intermediate views so that you have a smooth sequence. Otherwise, you'll get a very jerky sequence from 32 cameras. And actually, that view interpolation technique is based on stereo. What you do is you compute the epipolar lines between those two views, and then you know in the first view this point was here, and then in the next view it was here. And so in the intermediate view, you move it smoothly along the epipolar lines. So the view interpolation itself here is a stereo problem. Stereo is used, stereo geometry between cameras is used to do view interpolation. Okay, so you have 32 cameras. Between camera 1 and camera 2, maybe you generate 100 more frames, but through view interpolation. Then between camera 2 and camera 3, you generate 100 more frames, and so on. And then you paste it all together into one video. All right. Okay, so this is the case of object motion and camera motion, and it's we call this non-rigid structure for motion, and it's actually pretty difficult to do to estimate the motion in this case. I will not be discussing that in this course. That's an advanced topic. If somebody is interested, I can point you out to some references. Okay, but just the difference between these two cases. So this is rigid structure for motion. What do you have? You have a camera and you have a 3D object, and what you do is you take a picture, a projection of that object. So that's what you are given. Your knowns are here. I mean, you are given this image. You don't know that structure. Okay, that structure is something you want to compute, but you are given this image from the camera, and you understand this geometry of these are straight lines intersect, all meeting at the camera center and intersecting on this image plane. Okay, then you have another view of this scene, and the camera has moved, and then you have another view of the scene, and then you have another view of the scene. So that's your input. And from that input, you want to compute what the 3D points are like. Okay, as opposed to non-rigid structure for motion, in that you have a scene, and what you have is one view of that scene, and then as soon as you take the other view, the scene actually changes. The 3D structure actually changes. Then you take another view, the scene actually changes. Then you take another view, the scene actually changes. Okay, so what do you have to do then? Your input is this image and this image and this image and this image, but there is not one structure that you want to estimate from them. You have 4 images, and you have, well, in this case, you have 4 images and you have 4 different 3D structures that you have to estimate. And that is precisely the reason why this problem is hard, because you have 4 images and you have 4 structures to estimate it. It looks like it's the same problem as you have one image and you have to estimate a 3D structure from that, and we know we can't do that. That's an under constraint problem. An image will map, points in an image will map to rays, they won't map to a structure. They won't map to a unique point. Okay, so if you look at it this way, the problem seems ill-posed. There aren't enough constraints on the structure, and then all the methods that people have come up with in this field, they impose different type of constraints, again, assumptions of what the structure is going to be like. In our work, we impose that, well, yes, these are 4 different views and 4 different structures, but those structures have some relationship between them. It's a human, so the human will move smoothly. They will not deform randomly, and I can exploit that to have some more constraints into the problem to try to constrain a solution. Okay. So I'm just giving you an idea of this. I won't discuss the solution, but there is only one view per 3D configuration. That's why it's an ill-posed problem, equivalent to finding 3D structure from a single image. Okay. All right. But what we are going to do in detail is this one method of rigid structure for motion, which is rigid structure for motion means the structure is not going to change, and I have multiple images of it. And this is a method. This method is actually very. The reason I'm discussing this method is because of the elegance of the solution here. There are many other methods which work better than this method, and I guess we'll discuss one of them inshallah tomorrow. But I'm discussing it for various reasons. Number one, it's a very elegant solution. It shows you the power of linear algebra. It's purely a solution based on linear algebra. So I hope you can appreciate that, or I hope I can convey my excitement about this solution to you, right? It tells you how powerful mathematics is and how powerful matrix representations are, because it's like in one go you get this solution. Remember how difficult the problem is, right? I showed you those branches of the tree. They are moving all across each other, right? I have to take that data and resolve that into 3D structure. So somehow I have to encode in my solution the fact that if this branch moves faster than that branch, then that must be back and this must be, but it's not just that it moves faster, because if the camera rotates, everything will move, and the camera has to rotate in this solution actually. Okay, the history of this method is also interesting. This method is by and large known as the Tomasi and Kanade factorization method, which was proposed in 1992. Tomasi and Kanade paper is a very famous paper. It's highly cited. There are thousands of citations of this paper. It's written in textbooks and so on. It was considered like a very major breakthrough in this problem, because all the solutions before this to this problem were very unwieldy and mathematically complicated. They came up with a very simple and elegant solution. So this paper got a lot of attention. It turned out later that exactly the same solution was proposed 5 years earlier in Russia by a Russian mathematician. This guy wasn't like somebody working on computer vision. He was a mathematics professor. In fact, he won the field medal in mathematics, which is like the Nobel Prize of mathematics. So he's like a famous mathematician. And he wrote the solution exactly as written in Thomasian Kanade paper 5 years earlier. But it was a paper published in Russian because he was a Russian mathematician. So it was a Russian journal. And so kind of like nobody knew it. And now somebody translated that paper, and then and this paper has like thousands and thousands of citations, and this paper had like no citations at all. Nobody thought the paper was important. Maybe sometimes like weird things like that happen in science. In fact, in that paper, he described solution to two problems. Maybe he felt that this solution is like so trivial and simple that it's not worth one paper, so he wrote like I will solve two problems that occur in imaging geometry. He wrote in his paper. When we were doing our work in non-rigid structure for motion, we found this paper and then we cited it. So now this paper has a few citations, and that's mostly like our work citing this paper, and then other people kind of looking at our work and then citing this paper. Poor guy, he never got any credit for this work. But it is exactly the same solution. There isn't even a little bit of difference between the two papers as far as the mathematics is concerned. But it was not published in English. It was published in Russian language. Okay. Now, the way they formulated the problem is instructive for you to look at also as potential researchers in computer vision. What they did was they did some simplifying assumptions on the problem. So they did not solve the problem in its full complexity, okay, and that is what yielded a very elegant solution. Even though there is some approximations that they did, and so those approximations yield some errors in the solution, but nevertheless, it's a very stable and elegant solution. Okay, so the first assumption that they did, which is their critical assumption, is that they assume that the camera is not a perspective camera, it's not a pinhole camera, it's an orthographic camera. Okay, and you know that the perspective camera is a non-linear device. It has a division in it, but an orthographic camera is a linear device. It can be written purely as a matrix multiplication. You do not have to resort to P2 space to cater for that division, and that actually helped them a lot in the solution. This was one of the key assumptions that yielded some mathematical simplification, as you will see. Okay, then they need at least 3 images. So you have a video sequence, so that's not a problem. And then the scene has to be rigid, and then the camera has to move. This method will not work if the camera does not move. In fact, as we'll see, the camera actually has to rotate. It's not just that the camera can translate. Well, why is that? Because, well, if the camera doesn't move at all, then you have only one image. Because it's rigid structure, rigid camera. If you're taking a video, all the frames of that video is going to be identical. So it's really like a single image. So you can see that in this problem, the camera must move. Okay, but since they are using an orthographic camera translated does not change any disparity information. Okay, an orthographic camera translated is just like you take the 2D points and translate them in image space, because depth does not make any difference. And so it's not just that the camera has to move, but the method actually requires that the camera has to rotate. Okay, so there has to be a rotation R on the camera, and then they can do the solve. And of course, corresponding points have to be available. I have to track these points. I should know that this point number 1 in the image is in the next image it's here, and in the next image it's here. Okay. Now, if all those things are available, then we will take the solution. All right. Okay. So so how did the solution work? Let me first introduce some notation. Now, again, I'm using this as an example, not just to show this method, but generally to show you how problems are solved, because it's a really good example to do that. And my observation here is that notation is not a trivial thing. Don't think of, notation is just a way to write the same thing in different terms. Yes, it is indeed. But if you have correct notation, or if you have correct representation, it allows you to do more complicated things. It allows you to see further. Okay, an example of that is matrices. Everything I can do with matrices, I can do without matrices. because a matrix is nothing but a different notation to do some multiplications and additions, right? That's true, but that doesn't mean that matrices are useless, because everything I define in matrices I could define otherwise. Well, no, they're not useless, because that notation is so useful and so compact that it allows you to see further. You can do more complicated things now. Okay, think of it like this: your brain can only handle a limited amount of complexity. So if you make things simple, then you can do more stuff. Okay. All right, but so first thing you are doing on a problem, you want to solve a physical world problem, you should be able to represent that problem somehow. Okay, and that's why we have to do this notation. So the notation we are using here, because there are a lot of frames now, I'm going to say I have a video sequence of f frames. Okay, there are, like, let's say 100 frames in my video sequence, so f is 100, right? I have a video sequence of f frames, and now in each frame I have well, in 3D I have p points. Yeah, like this house, it has like p points on it. Okay, so p points will be seen in f frames. Okay, and I'm assuming that in every frame no point goes out of the view, no point occludes. Those are all real problems. It will happen in real problems that there will be points which get occluded, there will be points which go out of the frame, you don't see them, they go behind other points, so you don't see them. But I'm assuming none of that happens. Okay, just for the simplification of the solution here. So there are p points in f frames, and I can see all p of them in each frame. Okay, all right. So what's a world point? A world point I'll write by cap x, boldface cap x j. So j is an index of the world point. So that's xj, yj, zj, and that's the jth 3D point where 1 is less than equal to j is less than equal to p. So j is an index that goes from 1 to p. Okay, so let's say p is, well, let's just put some numbers here so we can kind of think about these things. So let's say you have 100 points and you have a video sequence of 300 frames. So, well, you have 100 points, p goes from 1 to, so you have 100 of these vectors xj. Okay, all right. And then you have small x, but I'm using two indices now, ij, because there is a small x for every world point, but it's also seen in every frame. So I'll have different values of small x. Let's say take the first point, but the first point will be seen in the first frame, the second frame, all the way to the 300 frame. So there are 300 representations of the first point in the image, and then 300 for the next point, and so on. So I'm calling that xj, which is small xj, xij, yij. I'm calling it xij, right? So that's a vector xij, yij. I should put really a transpose here just to be consistent with our previous notation. And then this is the projection of the world point xj in the ith frame. So the frame index is I and the point index is j. Okay, so how many points will I totally see? I will see 100 times 300 points, right? And this index I is the frame index, so it goes from 1 to f. F is the maximum frame index. In this case, I'm saying 300. So I goes from 1 to 300. Okay, is the notation clear? So because I have to deal with all these points, I have to be able to write them in my mathematics, and that's why I just introduced this notation. That's really the first step that you do in formulating a problem. Okay, and then we have some camera matrix pi. Now they are going to be, because there are f frames, each frame has a camera matrix. So there's going to be some pi, that's the camera projection matrix of the ith frame, where I goes from 1 to f. Okay, so there are going to be 300 of these camera projection matrices, except that this would in general have been a 3x4 matrix, but now I'm assuming it to be an orthographic camera, so it's not a 3x4 matrix. The third row I can cancel, so it's a 2x4 matrix. Really, it maps from a 4 vector to a 2 vector, so it's a 2x4 matrix. Okay, we have seen orthographic cameras in the previous module. You revised it because you have quiz today, so now you know it, right? Okay, all right. So that's notation. So I can say my xi's, the image observations, are related to the world points. The world points only have one index because they don't change. It's rigid structure for motion, so they have only one index. So the world point j is related to the image point j, but in the ith frame. So that's xij by the projection matrix pi. Okay, so this is a 3D scene point. This is the orthographic projection matrix. It could have been perspective, but they assumed in their solution to be orthographic for simplification. So it's an orthographic projection matrix, and this is a 2D image point. Let's just be sure that we know the dimensions. This is a 2x4 matrix because it's an orthographic matrix. This is a 4x1 vector. It's in P3 space. And this is a 2x1 vector because 4x2 times 4x1 is 2x1, which is directly an image point. Notice I don't need homogeneous coordinates here in orthographic projection because there is no division to be done later to correctly normalize the point. Okay, what does this matrix look like? So I can write this if I want to as an R pipe T, which is what we normally do, the extrinsic, and then the intrinsics, which is KO. We saw this form in the previous case. If I expand this out, there is some R matrix here, some T, which is minus R pipe C, and then I have X, Y, J, Z, I, all with an index J, and then KO is the orthographic matrix, which is this. So here I've written really a 2x3 times 3x4, which is what gives me a 2x4 matrix PI. All right. In fact, we saw this also that I can actually make this into a P3 vector and then write translation as an addition. And then I realized that I don't even need the third row of this extrinsic matrix. Okay. So this is also a form we saw before. Xij, Yij is simply this first two rows of a rotation matrix times XYZ plus TX, TY, the X and Y components of translation. The Z component doesn't matter. The analogy here is that you have this orthographic camera, all rays are coming in parallel. So whether you move this camera if to front or back, that does not change the image at all. Okay, because all rays are coming in parallel. So that does not have any impact on the image. So the Z row does not matter for the camera, right? Is that clear? It's just a revision of what we did earlier. Okay. So so this is really then what my model is. I'm still so what I'm trying to do now. Did I do that correctly? What I'm trying to do now is the first step was I defined some notation, and now using that notation I'm trying to come up with a model for my problem. In general, you do these things. So I'm describing this as a general problem of how you solve it. Okay. First, I'll come up with some model, and then I will solve that model. Okay, so I'm trying to basically model my problem now. What is how can I describe mathematically the problem that I just described to you qualitatively? Okay, all right. So this is our camera model now. Ri is the rotation I need for the ith frame of the video. What is the rotation that the ith frame has undergone? And it's two rows of a 3D rotation matrix. So it's a 2x3 matrix. Xj, I put a tilde now because it's a 3x1 vector. It's not a homogeneous entity. It's a R3 vector now. Plus Ti, which is a 2x1 vector, because the third element of T, which was Z, we dropped it. And that is what gives me the image observation if the orthographic assumption is correct. Okay, so this is the image projection of the jth world point in the ith camera. Okay, so this is the rotation, this is the image offset. And now they did a trick in their paper. It's actually a pretty crucial trick to simplify the solution further. So they said that what is this Ti here? This is just a 2D translation, right? Because it has two elements. So it's just a 2D translation of image points. Yani if the camera moves this much or it moves this much, the images are going to be the same except they would be translated somehow. Okay. Now this image translation does not tell you anything about 3D because it's an orthographic camera. So it does not contain any information about the problem that I want to solve. So it's just an unnecessary nuisance here. I'm just going to get rid of it. And how do I argue that I can get rid of it? I say, well, the origin of 3D world point is, I'm after computing structure, so I can choose the coordinate system that I want. Okay, so the origin of 3D world points will be at the center of those 3D world points. I don't know those points, so I can just assume the origin to be anywhere, and that origin is just going to be, let's say, the center of this point cloud, the mean of this point cloud. Okay, which means when I recover this point, I will recover them about a certain center. I don't know that yet. Okay, and then in the image, those 3D world points are projected into the image. So in the image, I'm going to assume that I'm not working with pixel coordinates. I'm going to assume that my origin of the image coordinates is the mean of the image points, which means it's also at its center. Okay, I'm just going to describe the image points about their mean, which means if you give me image points, you give me image measurements, I'm just going to compute their mean and subtract that from every point. And so now my points are about a center. Okay, now if I always do that, then if you translate the camera, nothing is going to happen to my points, right? If you translate the camera, the points are going to translate, but then the mean also translates by the same amount, and I always, whatever points you give me, I always subtract them from their mean in every frame. Okay, so which means the translation then has no effect. If I choose the image coordinate system in every frame such that the origin of the image points is at their center, then translation has no effect. Is that clear? Right? Because you move the points. By moving the camera, you move the points. By moving the camera, only 2D translation happens to the points, nothing else, for the orthographic case. And you move the points, but I say, whatever points you give me, I'm going to compute their mean and describe them about that mean. So I subtract the mean out. So which means my points remain the same if you purely translate the camera. Which means the camera translation has no effect. If I work in this type of coordinate system, camera translation has no effect and I can just drop it. Okay? So notice how we are making simplifying assumptions. Often in research, you are faced with a complicated problem, and you say, well, I can't solve that problem. It's a bit too hard, right? So you say, let me solve a simpler problem, and then even that's too hard. So you say, let me solve a simpler problem, and then you try to solve the simpler problem, and then you find the full properties of that problem and see how those simplifying assumptions you took, what is their impact, what limitations do you put on their solution. Okay. Well, also in research, often it happens that even the simplest form of that problem you can't solve. So then what do? You just say, okay, discard this problem and solve another problem. I'll work on something else. Okay. Researchers have that luxury because they can just pick the problem. In fact, just one more thing that I want to say there is that actually formulating the problem is often half the progress in research. It's not the solution. Even formulating the right problem is also half the progress. Okay. All right. So now what that means is if I have p 3D points in one image, in general that's the ith image, my model is just now xij is rixj. Okay. But now I don't have one point. I have like 100 of those. Okay, so I can write the first one, the second one, and third one, all the way to the 100 one, and because it's the same frame, I can just multiply them by one matrix, and all of them get multiplied. This is a trick you could use in your homework also that you just did. That if you have transformation to be applied to a lot of points, you don't have to write a for loop and apply them one by one by one. You can just concatenate all those points in a column matrix and multiply that transformation once. Okay, and what you'll get is so this thing is, what's the size of this? 3 by p multiplied by 2 by 3, because that's what R is now. It's 2 rows. Okay, and so you get 2 by p, which is all the image points in the ith frame. Okay, so this is one line, one matrix representation to write the projection, the imaging of all the p points in a particular frame. Okay, but now what do I have? I have a lot of frames. I have 300 of those. I have f of those in general. So I'm going to still write the whole thing. Okay, there was in my slides. I didn't need to write this. 2 by p, 2 by 3, 3 by p. Okay, and then I'm going to write all the P points in all the F frames in one equation. How will I do that? I will say for the first image I have an R1, for the second image I have an R2, for the third image I have an R3, so I'll just append R here. These will remain the same because they are not changing between the images, and I'll get a bunch of rows here. Okay, so that's the system that I have. I have R1, which is the first projection matrix, R2, the second projection matrix, all the way to RF, which is the Fth projection matrix. All of these are 2 by 3. Okay, so this one is really 2F by 3 because there are F frames. Okay, and this is still a 3 by P because the structure does not change. That's the key thing of a rigid problem, that this structure is not going to change. And then each one of these, this 2 by 3 multiplied by this gives me 2 by P here. Then this 2 by 3 multiplied by this gives me another 2 by P here, all the way downward. So I get a 2F by P matrix. Each one of these bold X's is a 2 vector. Okay, so there are F of those. So I have 2F rows here and I have P columns. So this is all my image observations in one go. This is the model for my entire imaging process. Okay, the whole video sequence imaged, the P points in the world imaged in the video sequence, all of them are written like this, given the simplifying assumptions that I took. It's an orthographic camera and translation is normalized and so on. Is that clear? So this is all part of the modeling process. I defined a notation in that I'm writing, because I was giving an input video sequence, I'm writing that video sequence mathematically so that I can manipulate it to find structure. Any questions? Is this clear? Absolutely clear? Okay. And again, it shows you the power of matrices. I wrote the whole video sequence in one matrix equation. The imaging process of the whole video sequence in one matrix operation. Okay. So remember, this is a 2F by P matrix. P points, so every point is a column. P world points, so every point is a column. And then 2F images, 2F rows, which are F images of that point. Okay, so essentially what you have is, if I draw these as blocks, essentially what you have is this view. You have a 2F by P matrix. This is really your measurements, because this is what will be given to you as input. Because you have image observations, you have corresponding points in images, so this is really your input. If you are given the input, you can fill out this matrix. Okay, so you have 2F by P matrix, which is your input. And this, we know, these are unknowns here. I don't know them, but I know that this is the form of the model. You have a 2F by 3 motion matrix, which is the rotations of the camera. You have 2F by 3 that, and then what you are after is really this guy, which is a 3 by P unknown matrix of the structure. So you want to recover that. Okay. So here I have completed my modeling of the problem. I have taken the problem and I've written it as a mathematical problem, as a mathematical model, and I exactly know what are my knowns and what are my unknowns in that model. Okay, my knowns are W, my unknowns are R and S. Right? So now I come to the third step, which will be, how do I solve this? Obviously, R and S are really some sort of decomposition of W. Okay, because I have to break up W to compose that into R and S. Just so that you are very sure you understand W well. So this was the video sequence that I showed you. One column of this of this matrix. This is the matrix, the image observation matrix. Each row, by the way, is normalized by its mean, because we are taking zero mean vectors. Okay, so each row is normalized by its mean. So what does a column really mean? A column of this image observation matrix W is one point of the 3D structure, because it's all the same point, P1. Okay, and that's one column of the structure matrix which we want to find. Agreed? And what's a row of this matrix? A row of this matrix is all the structure points, really, all the points, but seen in one frame. The first row corresponding to the first frame. The second, first 2 rows corresponding to the first frame, row number 3 and 4 corresponding to the second frame, and so on. Agreed? Is that fully clear? Right? Because we're going to do some math on this now, so I just want to make sure that you understand this. This is all I'm given in this problem now. All I have is this W. And somehow I have to break apart this W to find my R and S. I'm really interested in R. I'm really interested in S. R is just a byproduct of my process. Yeah. So the column of this image observation matrix is really one point, because how many columns you have? You have P columns, which are P points. So column denotes one 3D point, but all the images of that, which you see here. So a column is really this point and this point all the way concatenated to this point. Okay. So it's one point on this tree, but as you see it all through the sequence. Image observations. R is the rotation of the camera. Every frame has a different rotation. So R is 2f by 3. If it was a full R, it would have been 3f by 3, right? But because we have an orthographic model, we dropped the last row of R. So it's 2f by 3, where there are f frames. S is the structure. The first 3D point, the second 3D point. S is exactly what you generated in your homework, right? I asked you to generate a bunch of 3D points. So you generated a 3 by n matrix. Then you appended 1/4 row of all ones to it. And then you took its picture. So that's S. It's exactly that. It's the actual 3D points. And in fact, that's the unknown here. You want to solve it. In your homework, that was a known thing because you generated it, and so you were able to image it. But now you have the image and you want to solve for that S. Yeah. Image observations. Because each of this point is a 2D vector, x, y, right? So this is x1, y1, x2, y2, x3, y3. X1, y1, x2, y2, x3, y3, all the way to xf, yf. So that's 2. Each of these boldface is a 2 vector. So that's 2f by p. Okay, p world points, f observations. Okay, agreed? All right. Okay, so what do we do now? This is my model. I'm given W. I want to find R and S. Okay. Now I'm going to the third stage. The first step was I defined some notation so that I can talk about these entities. The second step was I wrote what my problem is, the model for that mathematically, which is this, W is equal to RS. That's the mathematical description of what is happening in my imaging process. Of course, with the simplifications that I took. There is a reason I took those simplifications, because it simplifies the solution, and so we are going to move to the next step, which is actually solving this. By solution, I mean here, I'm given a W, I want to find R and S. Okay? All right. So now the smart thing that they did is they came up with this observation, which is actually quite a simple observation. If I formulate the problem like this. So it's not that they thought of this observation and that's why they really formulated the problem like this because they can now make a simple observation. Okay, and that observation is that what is rank of W? Okay, so W is 2f by p. So rank at max can be the min of the dimensions 2f comma p, right? Because whatever is the minimum dimension, that's how many independent rows or columns at max you can have. So it's going to be no more than that. Okay. Now I took the example that f is, let's say, 300 and p is, let's say, 100. I have 100 points in a 300 frame video. So what do I have? I have min of 600 or 100. So rank of W can be at max. So it's really less than equal to 100. If W is a full rank matrix, in this case, full rank would mean rank of 100. Okay. But can W have a rank of 100? Is there a rank restriction on W that you see here? Anyone? What did you say? Louder, please. W is a multiplication of two matrices. Yeah. That's a very good observation. What he's saying is that W is really I know from my model that W is really a combination of R and S. It's a product of R and S. So the rank of W should be really the min of the rank of R and S, because it's a product, right? So if you have a matrix A times matrix B, if they are being multiplied, right, then A is, let's say, M by N, and B is really let's say A by B, right? Then the rank of the product, the rank of A times B, is gonna be the min of M and A B. Okay. It's not that I'm pulling this out of nowhere. I mean, let's just see that. Why does that make sense? How many columns does R have? It's 3, right? So think of that as 3 vectors. And then what does S do? S has a bunch of numbers here. Okay. So when they multiply, what happens? This, sorry, yeah, this column multiplied by this row, okay, to give me this element, right? So essentially, this element will be a linear combination of these 3 terms, right? It's a linear combination of these 3 terms. In what weight? The weight are given by S here, if I think of it like that. Now, what's the next term here? The next term is really this multiplied by the same 3 weights. So it's a linear combination of these 3 elements. So really, this entire column is a linear combination of these 3 columns in these weights, right? And then the next one is still a linear combination of these 3 columns in these 3 weights, and so on. So every column of W is really a linear combination of 3 columns of R. And so the rank of W can be no more than 3. If my model is correct, the rank of W can be no more than 3. Think of W as R just has 3 columns and S is just mixing those 3 columns in some weight ratio to create columns of W. So the columns of W are all not independent. They are all created from 3 columns, linear combination of 3 columns. In fact, what exactly linear combination? That's the column of S. The pth, the what should I say? The ith frame, which means the jth point column, which is the jth column of W, is created by the jth weights in S multiplied by the columns of R. Okay, is that the argument clear to everyone? So it's not a full rank matrix. In fact, it's highly rank deficient. If F and P are large numbers, this is highly rank deficient. You cannot pick all the columns in W independently or all the rows in W independently. That's not the case. It's coming from an imaging process, and that imaging process puts a very severe rank constraint on W. Okay. All right. Okay. So then the key observation here is that the rank of W is 3 really. If my imaging model is correct, the rank, I mean, the orthographic assumption is valid and so on, the rank of W can be no more than 3. Now, this happened, this simple rank came because of the simplifications that I took earlier. I took the simplification that it's an orthographic camera and I subtracted out the translation. If every translation point was different, then this wouldn't have been the case. But I subtracted out the translations and I did a orthographic assumption and so on. So I come up with a very simple rank here. Okay. In fact, other camera models also have a rank constraint on image observations. I think, I'm not sure, but for the perspective case, it comes out to be, W comes out to be rank 7, and then you put some restrictions on the perspective camera, and then you can reduce the rank till the orthographic restriction, then the rank is 3. Okay. All right. Of course, this rank constraints exist because S is the same. If it was non-rigid structure, then this wouldn't have been true. Okay. All right. So this is my model. And now I have observed about this model that W is not a full rank matrix. W is a rank deficient matrix. Its rank can at max be 3. Okay. By the way, a question here. Can the rank of W be less than 3 actually? How come? What if, so the rank of W can be less than 3 only if the rank of R or the rank of S is less than 3, right? The rank of R being less than 3 is difficult. If there are at least 2 frames there, then it can't be less than 3 because the 2 rows I know are independent of each other because they are orthogonal. But if there was only R1 and there were no R2, R3, R4, if you have only one picture, then rank of R, and then F would be 1, so rank of R would be 2. But if you have more than one picture, then the rank of R is at least 3. Okay? But the rank of S can be less than 3, right? How come? What's the case when rank of S will be less than 3? No, first answer my question. No, I have P points, but I say the rank is less than 3. How come? Yeah? Yes, if all the points are on a plane, then you give me an X and Y, I can tell you Z. Z is then entirely dependent on X and Y through the plane equation. So if 4 points lie on the plane, then rank of S will be, even though you have P points, you don't have less points, you have P points, but the rank of S will be 2. And if all the points were actually on the line, then the rank of S will be 1. Okay? So there could be a rank intersection. So the rank of W will be exactly equal to 3 if you have at least 2 frames and your points are spread in 3 dimensions, which means you have at least 4 points. Okay? Because 3 points are coplanar, so you have to have at least 4 points and they are non-coplanar. Then W's rank will be exactly 3, no more, no less. Yes, now you have a question. Yeah. Yes, that's true. That's true. So that, I mean, that's actually the reason why I want more images here. Okay. All right. In fact, so far I've seen that I need at least 2 images, but we'll see later that I need at least 3 images. There is another reason later in the solution that I'll need at least 3 images. Okay. So below 3 images, the solution will not work. Okay, so now I know rank of W is 3. So what? Right? So if rank of W is 3, then what will happen? What can you say about something then? Okay, yeah, let's just proceed. So what Tomasi and Kanade proposed is a factorization method. Okay, because this is really a factorization problem. I have to factorize W into a product of R and S. So it's really a factorization problem, right? And so they proposed a method in which I can factorize W. None of your standard factorizations would work. There is no well-known factorization in linear algebra that just breaks W into an R and S like this, right? So that's what they came up with. I'm gonna form an R and S out of this W, which will be the valid structure and the valid rotation matrices for that structure. Okay, so now I'm going into their solution. Okay, so far we saw how they modeled the problem and they observed something about the model, that W is a rank 3, and now we are going to form the solution. Okay, so I observed that W is at most rank 3. In fact, if my world points are spread in 3 space, they are not coplanar, then W is exactly rank 3. What I'm going to do is I'm going to apply my favorite decomposition in this course, which is SVD. I mean, there are a bunch of others that we have seen, like QR and RQ. But by far SVD beats them. We see that more often, right? So I'm going to just apply SVD on W. And because W has rank 3, my observation is that when I do SVD, there should only be 3 non-zero singular values. All the rest should be 0, right? That's what happens in SVD. The singular values corresponding to the null space come out to be 0. So the span of the space here is 3. The vectors of W span a 3 space, and so there should be only 3 singular values, right, which are non-zero. So I'm going to keep only the three singular values which are non-zero to obtain r hat and s hat. Okay, what does that really mean? That uh, what does that really mean? That when I do SVD of W into a USV transpose, right? That's what I'll do. Okay, so what would be the size here? W is 2F by P. Okay, so U will be an orthonormal matrix which is 2F by 2F, right? V itself, I'm writing the dimension of V, not V transpose. So V itself will be an orthonormal matrix which is P by P. Well, V transpose will also be P by P because it's square. And then S will be the matrix in the middle which will be 2F by P. Okay, and the P singular values, because at max the rank can be P, so the P singular values will be along the diagonal of this 2F by P matrix. I'm assuming P is less than 2F. Okay, so there will be P singular values along the diagonal, but if you sort them by their magnitude, only the first three will be non-zero and the rest should be zero. Now in real case, when I have real image observations, I'll get the rest also as non-zero maybe, but they will be much less in value than the other one. They will be smaller in value, and that's just because of noise or because of your wrong assumption that the model was orthographic. In reality, the camera has a bit of perspectivity to it. Okay, so so what I can do now is, because S is like this, which is like three values and all the rest are zero. Okay, so then this whole row is zero, this whole row is zero, this whole row is zero, this whole column is zero. Other than the first 3 by 3 block, everything is zero. So I really don't need a P by P V transpose, because only the first 3 rows of P V transpose will multiply with those 3 values, and everything else will be getting multiplied by 0. And similarly, I don't need a whole 2F by 2F U, because only the first 3 columns of U will be relevant because they are being multiplied by something non-zero, and everything else is being multiplied by 0, right? So I can make an R hat which is a 2F by 3 U here. Well, okay, let me first say, I'll make a U prime, which is just the first 3 columns of U, which is 2F by 3. Okay, and I'll make a V prime, which is just the first 3 columns of V, or the first 3 rows of V transpose, which is P, so it's P by 3 if I don't write the transpose, only the first 3 columns of V. And I'll make a S prime. Well, I shouldn't really write this S because that's bad. I have an S for structure and now I have an S for the diagonal. So let me write it as D for the diagonal matrix. So I have a D prime, which is only a 3 by 3 matrix. Because I just took the first 3 by 3 block here, everything else was 0. So that's not, so I dropped those rows, I dropped those columns, so I can just drop these, which will getting multiplied by those rows and columns. Okay, and now the dimensionality is correct, 2F by 3, 3 by 3, P, 3 by P because it's transpose. So that gives me a 2F by P, which is what W is going to be. So I just dropped the useless terms out of this SVD decomposition because I know that I have a rank restriction here. Okay, so this is really the mathematical way of exploiting that rank restriction, doing a decomposition that is cognizant of that rank restriction by dropping the 0 rows and columns. Okay, now I do that. I know that, okay, these are 3 matrices now. U is the correct size. I wanted R to be 2F by 3. U is indeed 2F by 3. And then V is also the correct size because I wanted S to be 3 by P, and V transpose is indeed 3 by P. But there's a 3 by 3 D prime in the middle. So what I can do is I'm just going to do U prime is U prime times D prime square root, and then D prime square root times V transpose. Let me call this R hat and let me call this S hat. Okay, I just took that 3 by 3, broke it into 2 matrices, multiplied half of it there, half of it there, and my decomposition is valid. Okay, so I get something which is the correct size. I get an R hat and an S hat, where R hat is 2F by 3 and S hat is 3 by P. Yeah. Okay, yeah, you have a valid question. I could have just multiplied d this way or that way, or I could have taken 1/4 of d this way and 3/4 of it that way, and all of them would have been valid. There's really no restriction that I should do it half and half. Yes, the decomposition is not unique. D can be divided many different ways. Any product that results in the D, any 3 by 3 decomposition of that results in a D is a valid decomposition here for D. Yeah. So far this is not structure, by the way. I did a mathematical decomposition. The decomposition doesn't know that this is structure, right? And it doesn't know that this is a rotation matrix. I labeled it R hat. So you kind of think it's kind of like R, but well, it's any 2f/3 decomposition. It might not be your actual rotations that the camera has undergone. There is no imposition in the solution right now to say that these are rotation matrices. And there is no imposition to say this is the real structure. Yeah. Yes, but what is orthonormal here? The columns themselves, not the rows. The rows are only 3. So the first 3 elements and the next 3 elements are not going to be orthogonal to each other because the whole row was orthogonal and you dropped all of that now. Okay. Now D is a diagonal. Okay, so the columns of U prime are orthonormal to each other. D is a diagonal. So basically what you have done is you have scaled those columns, which means their normality would be distorted now because it's scale factor of 1. Okay, but orthogonality does not change if you just change the length of the vectors. So they are still orthogonal columns, but not normal. They don't have a norm of 1 because now they are multiplied by the square root of the singular value. Okay, all right. So now comes the only tricky part in this solution. This R hat and S hat is not my real solution. It's just some decomposition of the correct size. Agreed? So it's not my real solution. But my claim is that this must differ from the real solution only by a 3 by 3 linear transformation. I'm calling that Q inverse. Okay? So essentially what I'm saying is that R hat and S hat do multiply to W because I broke out W to get them. So they do multiply with W, but they are not the correct R and S. There's no guarantee that they are correct R and S. But my model says that the correct R and S do exist, right? So what I observe is that inside R hat and S hat, I can multiply by a 3 by 3 transform Q inverse. Well, that I can always do because Q inverse is identity. And then R hat Q is like a new R hat prime, and Q inverse S is like a new S hat, that's like S hat prime. Now because there exists a correct decomposition, how do I know that? I know that from my model. So because there exists a correct decomposition, therefore there must exist some Q that gives me that correct decomposition. I don't know what it is, but there must exist some correct Q that when multiplied by R hat, post multiplied by R hat, and Q inverse when pre-multiplied by S hat gives me the correct R and the correct S. Right? Because the correct does exist, and so that would also be a decomposition. And the decomposition can differ by this internal matrix because that's an identity. So there must exist some Q and Q inverse here that I can find. I don't know how to find it, but I can find so that I get the correct R and the correct S. The R that actually corresponds to camera rotations and the S that actually corresponds to the structure. Okay? Is that argument clear? Okay, so that's good. So that now the whole problem of finding structure becomes just the problem of solving for Q. Okay? So how can I solve for Q? I mean, there could be an infinite number of different linear transforms and infinite number of 3 by 3 matrices that are Q. One of them is correct. How can I find the correct one? What's the constraint within the problem that will help me do that? कौन सा proper matrix? No, but you will get the image points from R hat, S hat anyways. And you will get them from any Q that you pick which is invertible. Right? Because Q inverse is just identity. So give me any Q which is invertible. The only condition I'm making is it's invertible, it's non-singular. Give me any Q, my R hat and S hat will still give me W when multiplied inside by Q inverse. So that's not a constraint. I'm looking for some constraint that will tell me this Q is better than that Q for the purpose of finding structure.
R should have no, the rotation matrix should have no.
Precisely, that's very good. The rotation matrix is not an arbitrary matrix. It has some rules. What are the rules for that? Each row of a rotation matrix has norm 1. And each two rows are mutually orthogonal because two rows are in a rotation matrix. So row 1 and 2 should be orthogonal, row 3 and 4 should be orthogonal, row 5 and 6 should be orthogonal because each one of them are coming from a rotation matrix. Now I have an R hat that does not have this property in general. By the way, why doesn't it have that property? I got R hat from SVD, so SVD is supposed to give me orthonormal matrix. So shouldn't they be orthonormal to begin with? Well, so maybe I shouldn't. Maybe I just multiply D on the S side, and then isn't that the correct valid R? It's that the three elements of R are not orthogonal this way because the whole row was supposed to be orthogonal and normal. I just took the three elements, right? So there's no guarantee of orthogonality or normality on those. It's actually this way that those columns are orthonormal still. If I don't multiply by D, they are still orthonormal. But that doesn't help me. I'm saying the constraint is this way. The first two should be orthogonal. So this gives me a constraint on Q. I'm not looking for any arbitrary Q. Every arbitrary Q here, which is invertible, will indeed give me W. But I'm looking for that particular Q, which will make this orthonormality property of R. Okay? So now that's my problem only. That's all that I'm left with. Okay, so the observation is that the correct Q will result in an R whose rows are pairwise orthonormal. Now this is like, now you give me a Q, I say, oh, this is not a good Q. This doesn't make it orthonormal. Now, aap mujhe Q dein, I'll say, oh, no, this doesn't work. Now I can try to find for the correct Q because I have a criteria for the correct Q. So let me write that. So the observation is that R hat Q, I want the Q such that R hat Q will result in an R which has this orthonormality property on pairwise rows. Okay, so the ith image will result in the following three constraints on Q. I've written the pairwise orthonormality in it's a kind of a weird notation, but I've written that constraint mathematically now, right? What am I saying here? What am I saying here? R, the two rows of R, let's say row 1 and 2, should be orthonormal, which means those two rows times these two columns, the transpose of that should give me 1, 0, 0, 1. Okay, R is a 2 by 3, so I multiply 2 by 3 by a 3 by 2, the transpose of itself, so it should give me a 2 by 2 identity. That's the orthonormality constraint. This is what I've written mathematically. R 2i minus 1 colon 2i, that's just row number, let's say 5 and 6, 7 and 8, right? Because if I is 4, then 2i minus 1 is 7 and 2i is 8. So that's just a way to write a pair of rows. So R 2i minus 1 colon 2i times R transpose 2i minus 1 2i should be I 2 by 2. That's the way to write the orthonormality constraint. But then since R is R hat Q, so that means R hat, I already have R hat because I did my SVD decomposition. So I already have R hat, I don't have Q. But R hat 2i minus 1 colon 2i times Q, and then R hat 2i minus 1 colon 2i times Q transpose should also be identity. And this gives me the constraint to solve for Q. Okay, so this is called the orthonormality constraints. I opened this transpose, so I got this thing. So R hat 2i minus 1 colon 2i Q transpose R hat 2i minus 1 colon 2i transpose. This should be identity 2 by 2. I've written here that these are 3 constraints and not 4, even though I 2 by 2 has 4 terms. So this should really be 4 equations. right? I2 by 2 has 4 terms. So there is one equation which says this row times times that column with the q in the middle equal to 1, because 1 is one of the elements of the matrix. Then the second one, so that's the second row with its transpose with the q in the middle should be equal to the second one, and then the first with the second should be 0. But really the other 0 is a symmetric of that. It's the dot product of A with B is the same as dot product of B with A. So those zeros along the diagonal are actually the same constraint. I mean, there are really 3 constraints. First, that the first row of R should have norm 1. Second, that the second row of R should have norm 1. And third, that the dot product of first and second rows should be 0. Okay? There isn't a fourth constraint that the dot product of second with first should be 0, because that's the same. So really you get 3 constraints from this equation. Okay, these are 3 linear equations. You already know, you have ample practice now on how to solve linear systems. So these are 3 linear equations. You will separate out the unknowns of Q. You will write the R terms here, the R hat terms here, and then you'll solve that system. Okay, except you have a QQ transpose in the middle. So really what you have is, because you have 3 constraints from every camera, and you have F of those cameras because you have F frames, so you have total 3 F constraints on QQ transpose. Now, because Q is a linear matrix, you have QQ transpose. So QQ transpose combined is a symmetric matrix. Anytime you take a matrix, you multiply it with transpose, its own transpose, you get a symmetric matrix. So a 3 by 3 symmetric matrix has 6 unknowns because the other 3 are the same. The 3 along the diagonal, 2 along the next diagonal, and 1 along the next diagonal. So you have 6 unknowns. So QQ transpose has 6 unknowns, and you have 3 constraints, which means you need F at least equal to 2 to be able to solve this. Yeah. Okay. So I shouldn't have really said 3 cameras. It's actually 2 cameras. Okay. And how do we solve this actually? So you can solve it as a linear system rather than a Q. If you want to solve directly for Q, then it's a quadratic system, because QQ transpose is like Q squared. There are going to be Q square terms in this. But you can just say that G is equal to QQ transpose, which is a symmetric matrix. Now G has 6 unknowns. So you solve it linearly. I should really change this F greater than equal to 2, because there are 3 constraints coming from each F, right? So you solve for G linearly. And then once you have G, you want to find Q. You just need a decomposition that breaks a matrix into some matrix times its own transpose. And that's actually, in linear algebra, that sort of decomposition exists. It's called Cholesky factorization. So that's like the 4th factorization that we have, no, 5th factorization that we have hit in this course, right? We know eigen decomposition, we talked about that. We know SVD, we know QR, and QR's sister, which is RQ, right? And then now the 5th one is Cholesky. These are all standard factorizations in linear algebra, so I don't have to tell them. You can just look up a package to do Cholesky factorization. So the argument here is this: I will solve not for Q, because that's a quadratic system. I will solve for G, which is a linear system, but G is equal to QQ transpose, so now it's a linear constraint equation. Okay, I have R hat. I will solve for G that satisfies this constraint. Once I get G, I will transform that into QQ transpose by Cholesky factorization. So I get Q. Once I get Q, I will post multiply that with R hat and pre-multiply Q inverse with S, and I'll get my R and S. That's it. So it's all like linear algebra, right? There is no. So there are some limitations here. Let me just wrap this up. Orthographic camera is assumed. Now, in reality, if your camera is not orthographic, well, we know when an orthographic camera can approximate a perspective camera, when you are far away zoomed into the object. So this will only work well if the camera focal length or the distance of the camera is large compared to the depth variation of the object. If I'm really close to objects and I'm moving around them compared to their depth variation, then this method is going to not work very well. And then structure recovery is only up to a rotation. Let me explain that comment. This is my constraint, right? So this constraint, I can ask myself, is R unique? Is Q unique here now under this constraint? And actually the answer is that no, it's not unique, because if I have some other 3 by 3 matrix R, I have, in the constraint, I have QQ transpose, right, as the unknown here. Now, is that a unique choice or not? If I have some other matrix R, any 3 by 3 rotation matrix R, I can define R transpose here as identity, because the rotation matrix has its own transpose as its inverse, and then this thing becomes a new Q. Q times R becomes a Q prime, and R transpose Q transpose becomes Q prime transpose. And so that new Q prime will also be a valid solution to this constraint. So the orthonormality constraint, this constraint does not give you a unique Q. All Qs that are equivalent up to a rotation matrix, a 3 by 3 rotation matrix, are actually equally good to satisfy this constraint. Which means my structure recovery will only be up to a rotation. I wouldn't know I'll get the correct structure, but it can be rotated, because I'll pick one particular Q out of all those possible Qs that are different by an R. Okay? Which is kind of okay. If you got your house recovered properly, but it was just rotated, it's kind of okay, right? It's still good structure. And the translation component in the direction of the optical axis, that cannot be recovered. Yeah. In fact, that's a very good point. Technically speaking, all that says is that the choice of the world axis around which you describe those points is arbitrary. We never fix that. We never fix the rotation of that. We actually fix the translation of it, but we never fix the rotation of that. Okay. Finally, I'm just repeating what we said as in one go. The input is a registered measurement matrix W, computed from P features tracked over F consecutive frames. Okay. Step number 1, compute the SVD of W. That will be U, D, V transpose, where U is 2F by 2F, V is P by P, and D is 2F by P diagonal matrix of singular values. Set all singular values to 0 except the largest 3. They should really be 0 if the model was accurate, but they will be non-zero because these are noisy measurements and the model itself is not accurate. So I just keep the first 3. They are sorted, so I just keep the first 3 and make all the rest 0. Now use these singular values to compute U prime, D prime, V prime, where D prime is the top 3 by 3 matrix of D, and the 3 highest singular values, containing the 3 highest singular values. U prime is 2F by 3 matrix, and V prime is P by 3 matrix formed by the corresponding columns of the singular values. Okay. Then compute R hat, which is U prime, D prime half, and S hat, which is D prime half, V prime transpose. Okay, so I got my R hat and S hat. Then solve for Q using the orthonormality constraints, which are every frame gives you 3 constraints, and then the output should be rotation and shape matrices given by R hat Q and Q inverse S hat. D. Sorry? No, D half times D half is equal to D to the power half times D to the power half should be equal to D, right? So D is a diagonal, let's say A, B, C along the diagonal. So D half is just along the diagonal you have square root of A, square root of B, square root of C. That's it. Because this multiplied by itself will give me this. No, no. In general, the question is, I need only 2 frames. So if I use only 2 frames and I have a lot of video, should I use only those 2? And no, because the nature of the solution is that the more the constraints you can, because you are solving for Q, if you use only 2 frames, you're only going to put 6 constraints on U, and G has 6 unknowns. So that's just a critically constrained system. And we know that the more you constrain your system, the more constraints you can put in your system, the more stable your solution comes. That's the nature of least squared solutions. And this will also come out to be a least squared solution. You'll solve it through the pseudo inverse. Okay. So in general, you should use all your data. Okay. This is, by the way, in least squared solution in general, yes, you should use all your data. But what if some of the points are wrong in your data? Then your least squared solution is sensitive to noise. It gets thrown off. And when we do the next module, we will see. I will talk about robust estimators, some techniques which work even. They're not least squared solutions, but they work even when there is a lot of noise. So we will. That's a topic which is very important, and we'll discuss that. Yeah.
Why did you divide your D into square roots if you were going to find the Q anyways? If you just divided D on one side,
Yeah.
you could still find your Q.
That's a correct observation. I really do not. There's no requirement. I really do not have to do D half and D half. I could do D 1/4 and D 3/4. I could do D 1/5 and D 4/5. I could do D all the way this way and not on that way, or all the way that way, not this way. All of them are valid decompositions. And for all of them, there should exist a Q which balances out to the correct solution. Okay. Finally, I want to show you results. So here's a sequence that I showed you in the beginning. We are not talking about tracking methods. Actually, it turns out this method is so simple that, I mean, coding this is like 10 lines of code. So, well, maybe even less, I think. So really, the method is very simple and elegant, right? The challenge actually becomes in tracking so much points to find a W where there is no occlusion happening and there is perfect correspondence and so on. So I'm showing you results where there was actually a very sophisticated method to make that W matrix automatically. A lot of points were tracked very successfully, and that's a method. But once you have W, the rest is very simple, and this is the result for that. So that's the recovered 3D structure. Okay. Now this is, I find this very fascinating because this is just linear algebra. I mean, this is just SVD and then a little bit more on applied onto that SVD, another SVD, some least square solution. It's all linear algebra. Somehow, just through abstract mathematical techniques, you were able to recover all the 3 points very well. Yeah. No, it's just because of the points are all the same color, but it's just being perceived here because of the density. You don't see the points on the tree so much. I see them better on my screen, but it's just because of the density of points. I mean, there are a lot of white points together, so that is appearing on the screen as a brighter color. I mean, there were a bunch of points which are selected, and then they were tracked through that 100-frame sequence, right? So it wasn't that every pixel was tracked. Some points were selected which were conducive to tracking, and then if we were unable to maintain that track for 100 frames, we just dropped it. Okay, so there's quite a sophisticated tracking method behind this. That's the challenge in doing this at this density. But then once you have your W, this reconstruction is pretty automatic. Okay. All right. Okay, done. I'm sorry we went over time, but I want